The recommended cutting speed for mild steel is 20 meters per minute. To express this as a spindle speed in RPM, we need to use this formula. N, which is the spindle speed in revolutions per minute, is equal to 1000 multiplied by the cutting speed in meters per minute. This is to convert it to millimeters, so that it is in the same units as the drill diameter. This is then divided by the circumference of the drill being used, which is pi times the diameter of the drill in millimeters. So, to put this into our example, we have 1000 multiplied by 20, which is the recommended cutting speed. This is equal to 20,000. We now divide this figure by the circumference of the drill, using pi as 3.142 times the drill diameter, which is 10. We get 31.42. This divided into 20,000 is equal to 636.53. We can round this up to 637, which gives us the recommended spindle speed in revolutions per minute to which we need to set our drill. However, we may not always be able to set this speed exactly on the machine, as the spindle speeds are governed by pulley or gear ratios. We therefore have to select the nearest setting available. To take another example, if we require to drill a hole of 15 millimeters diameter into a piece of cast iron, we know from the table that cast iron should be drilled at a cutting speed of 25 meters per minute. Putting this into our formula, N is equal to 1000 multiplied by 25 divided by pi times 15, which equals 25,000 divided by 47.13. This gives us an answer of 530 revolutions per minute. If you are using a sensitive drilling machine, then the feed of the drill through the workpiece is governed by your own feel of the way in which the drill is cutting. You do, however, need to make the drill cut. If you do not put enough pressure on the cutting edge, it will just rub against the workpiece and overheat. This will take the cutting edge off and blunt the drill. On the other hand, if you apply too much pressure, you run the risk of overloading the drill and breaking it in the hole. Where the machine has the facility for a power feed, this may be expressed in terms of a feed rate of millimeters per revolution, or millimeters per minute. In either case, this refers to the vertical distance travelled by the drill. In the case of our two previous examples, we would again need to look up the recommended feed rate for the particular material we are cutting, and also the drill diameter being used. The appropriate feed rate is then set on the machine and the feed engaged. You must be aware that these figures for both feeds and speeds, derived from the calculation and tables, are but a starting point. They are not cast in stone. Many other factors will affect the efficiency of the cutting action, such as the rigidity of the machine, the rigidity of the work-holding device, the depth of hole to be cut, whether or not any coolant or lubricant is being used, and whether you have judged the hardness and toughness of the material being cut to be correct. You may find from trial and error that you can increase or decrease these settings according to the results that you obtain. The type of drill you are using is also a major factor. These examples have been based on high-speed steel drills. If you are using a lower or higher specification than this, then the figures must be correspondingly adjusted.